All right, good morning, folks. Happy Wednesday. I know this week has been a lot of work for you folks. So we're gonna jump right in and get started with 13.1. So we are starting a new unit today. It is going to be on plane curves, which is parametric equations, and polar curves, which deals with polar equations. So that's going to be the first half of this unit. And the second half of this unit is going to be a lot of different types of applications for integrals. So I know we worked in a very abstract realm where we're like finding all these integrals and taking derivatives and finding slope and things like that, but without like a real like here's what you could use it for. So the second half of this unit is a lot more like here are some applications for the stuff that we've been learning to do. Okay. So without further ado, let's go ahead and get started. Okay, so I'm going to go ahead and share my screen. And we are in 13.1. That's what we're going to be covering today. All right, there we go. Okay. So 13.1, I wanted us to start off as usual, think about some things that we know, and then think about how things might be a little different or extensions of what we've already learned, okay? So let's start with this what we know category. So what we know things like y equals mx plus b. What shape is that if you were to graph this?
A line.
It's a line, right? And we know that. We know that inside out, we can graph a line any day of the week and be totally fine. What about y equals x squared? What shape is that?
U. Parabola.
Exactly, we get a parabola. Okay, so those two are pretty straightforward. What about this third one here? What shape does that give us?
Circle.
And the fourth one?
Yeah, I'm connecting them right now.
Hyperbola.
A hyperbola, yeah. And then the last one actually gives us the same shape that that second one did. We also get a parabola from this. Okay, so that's just a smattering of the functions that, as you've gone through your academic career, have been really sticky, things that you want to know what they look like. And so when we think about all the graphs that we've done them on something called a rectangular plane. Okay, so a rectangular plane has the x, it has the y. If you wanted to be a little fancier, you could call it a Cartesian plane. Okay, but a rectangular plane and a Cartesian plane are the same thing. It's our regular xy axis. Now, just as well as you know all of these shapes, a line, a parabola, ellipse, hyperbola, and all the other shapes that you know for a rectangular or a Cartesian plane, our goal is going to be thinking about different coordinate axes. Okay, so the first one we're going to start off today is what happens if we graph something that actually has a parameter. It's not just an x and a y, but there's actually a third variable, t. Okay, and then next week we're going to get to ones where we have an r and a theta, and we'll talk about other ways of graphing different curves. Okay, so in this coordinate plane, we still have the x and we still have the y. Okay, But what's different is x is actually some function of a parameter, t. And y, similarly, is a different function of that parameter. So we can say x equals f of t and y equals g of t. Now, what we're going to be focusing on today is graphing parametric equations, okay? So we're going to learn how to graph them. We're going to learn how to graph them using tables, so like you did way back when you first learned how to plot xy points. We're going to learn how to graph them using eliminating the parameters, so getting it back to equations that look more like the left-hand side. And then we're going to take a look at representing a rectangular function with multiple kinds of parametric functions. Okay, so what we're getting into is a situation where there's no longer just one name for a given shape, but it's going to be more like we saw with the parabola, how we could describe it as like an x squared or an extension of that. Okay, and similarly, there's different ways to call lines, but when we talk about these rectangular equations that we have, we're going to be able to give it more than one parametric equation that defines it. And as messy as that sounds, what that gives us is a lot of options in terms of easier ways to describe curves that maybe when we look at the rectangular or Cartesian equation for it, that equation might be really complicated. Okay, but the biggest application for parametric equations is exactly coming from this t. Okay, so a lot of times we want to think about how things move over time. And it's easier for us to describe that movement as sideways movement over time and vertical movement over time. Okay, so sideways and vertical movement over time is a great application for parametric equations. Okay. So let's take a look at these few pictures. So you have different kinds of curves, okay? So curves can be any kind of shape. So like A is a good example of just a curve, some curve. And B is something where we could call that specifically a closed curve, okay? And it's closed because we can find a region inside of that. Okay, so we could break it up into like that closed off part and this closed off part. Okay. And then if we take a look at this last one, this is just an example of a simple closed curve. And a simple closed curve just means on the inside there is one region, a single region. And that is something that we could find the area of, okay? Now, if we look at a sort of textbook definition of parametric equations, okay, this is what it might be a little bit more formally. So we're going to let C be the curve consisting of all ordered pairs f of t and g of t, where f and g are defined over a given interval. Okay, so maybe we're saying the interval is just like from 0 to 2 pi, or maybe it's just from 0 to 10, like the first 10 seconds of the movement of something. Or it could even be all real numbers. It could say like for the expanse of time, we want to define these two functions. And so we would say these equations are x equals f of t, y equals g of t, for all t in the interval. And these are called parametric equations. And the parameter is t, okay? All right, any questions so far?
I have a quick question when we get to our first example.
Okay, all right. Do you want to ask your question now or you want to ask it after?
Yeah, just real quickly. T is time. We're seeing how this graph changes over a period of time, right?
Correct.
Can time be negative?
It depends on what you consider your starting moment. Maybe you have a starting moment and it could be something before that happened.
Okay.
And that might be one way to use that.
Okay.
Okay. So let's take a look at some graphing of parametric equations, okay? So here we have a set of parametric equations, x of t, and we have y of t. And so when we have parametric equations, we want to make sure that they come in a pair, that you have an x and a y. And then you want to know what kind of x values, or sorry, what kind of t values you're going to be plugging in. All right, so in this equation, I went ahead and gave you the table. So we've got -2 because that's the starting t value. And then I just counted by ones all the way until I got to the end, which was 3, okay? Now, we're not always going to count by ones. And so that's something that I just want us to be really clear about. We're not always going to count by ones. In fact, some of the later examples, it's going to be easier if we count in different intervals, okay? So all we're going to do is we're going to take our t values and we're going to plug them into the x and the y equation, and we're going to fill out the table below. So for example, x of t, when t equals -2, is going to be -2 squared, which is 4, and then 4 minus 4, which gives me 0. Okay? And I can keep going down the table. I can plug in -1, 0, 1, 2, and 3. And when I do that, I will get the following values: -3, -4, -3, 0, and 5. Okay. Now for the second column, I'm going to take all the same t values and I'm going to plug them into the y of t equation. Okay, so we have that as y of t equals t over 2. So in the first line, when I put in -2, I will get a -1. When I put in -1, I'll get -1/2, 0, 1/2, 1, and 3/2. Okay. And so now we're going to take each pair of blue and pink points and we're going to plot them on the graph below. Okay, so the first point I'm going to graph is 0, -1. So I'm going to go to 0 and go down to -1. Okay, and there is my starting point for this given interval. And then I'm going to plot all the other points. So I've got -3, -1/2. I've got -4, 0, -3, 1/2, 0, 1, and 5, 3/2. Okay. So I plotted all 6 points that I had in the table. Now, when you connect them though, like, so if we think about a parabola or a line, and when we graph them, we normally just go ahead and put arrows on both ends to show that it extends forever and ever in both directions. But one thing that's going to be really different about graphing parametric equations is we want to make sure that we indicate the direction in which this curve gets traced. So I started down here and I went in this direction, and then I went here, okay? And since that's the interval, I stop. I don't have arrows on both ends because that's it. That's the whole graph. But I can go ahead and add some arrows on the graph that show me the direction in which I trace those points, okay? So that's sort of something that's a little bit different about how we graph the parametric equation. We actually care about the direction, whereas in a regular rectangular equation, we don't really care about the direction, okay? All right, is this graph a function or not?
No.
No, how do you know that?
Horizontal line test.
No, yeah, VLT.
Not continuous?
It is continuous.
The VLT.
Yeah, the vertical line test, right? So vertical line test is the one that tells us a function. The horizontal line test is the one that tells us if it's one-to-one or not, okay? So this is not a function. So when we refer to parametric graphs, we really want to be careful about our language here. So you'll notice that I try at least to call it a curve and not a function, because a lot of the pictures that we're going to generate are not actually going to be functions. Okay, so fails vertical line test. All right, so from here, let's take a look at this idea of eliminating parameters, okay? So what I mean by that is when we take a look at parametric equations, if I said x equals t squared minus 4, y equals t over 2, I don't know that I would know immediately what that looks like. I might imagine, oh, kind of looks like a parabola because I see a t squared, but we just don't work with parametric equations as often as we do rectangular ones. So it's okay that at this point, we don't really recognize what they are necessarily. And so let's eliminate the parameters. And so we're going to end up with the rectangular form of this function, okay? Or not of this function, of this curve. So let's take our parametric equations down here, okay? And I'm going to write them as x equals t, nope, x equals t squared minus 4, and y equals t over 2. And so when we say eliminate the parameter, our goal is to end up with one equation that does not have any t's in it. So we want to eliminate or get rid of the parameter, which is t. And so what I do is I look for the t that is the easiest to isolate, and then think about how I can plug that t into the other equation so that I can get rid of any t's there. So I noticed that this y of t is, I could isolate t by just multiplying both sides by 2. And so what that means is everywhere I see a t, I can replace it with 2y. So that's going to give me x equals 2y squared minus 4. Okay. And I could go ahead and distribute this a little bit. So I would get x equals 4y squared minus 4. And just because we learned very recently the new form for a parabola, let's solve for this in the form that we just learned in the previous chapter. So I'm going to add 4 to both sides. And then I'm going to divide by the 4 attached to the y squared. Okay, now that form is something that's very familiar to us. We know that this plus 4 moves our parabola to the left 4 units. And we know that this 1/4 would help us find the focus if we wanted to find the focus, okay? But we also know, because it's a y squared, that this is a sideways parabola, okay? That has been shifted to the left 4 units. And that looks a lot like the picture that we have here in the purple, okay? The one difference here is that this is our graph, but we only have part of this curve. So we don't have the whole y squared equals 1/4 x plus 4. We only have the section of it that corresponds to a certain parameters from -2 to 3, okay? So plug numbers into a table, plot the points, eliminate the parameters, and there are a lot of different ways to do this. I'll try and highlight some of the key strategies that we can use here, or sort of why I choose different ways. But again, we might all have different ways of seeing the equation, so our eliminating the parameters might take on might look a little bit different. Okay. All right. So what we're going to do now is we're going to take a look at the second example. Okay. So here I have x equals 4t squared minus 4 and y equals t. And I'm going between -1 and 3/2, okay? So what I'd like us to do is actually start with a little table here, okay? So I'm gonna go ahead and make a table horizontally, but it doesn't matter which way you make it. All right, so we've got our parameter. We're going to have some x values and we're going to have some y values that correspond to those. Now, the first t value that I should put in there is -1, right? Because that is the beginning of the parameter that I have here, -1. And I'm going to count by the same amount that I counted in the previous. So I'm going to count by ones, all right? So I've got -1, 0, 1, and then I'll finish off with the 3/2, okay? And so let's plug these numbers into our parameters. Now the y one is super easy because y equals t, so I can just bring those numbers right down, -1, 0, 1, and 3/2. And the x1, I do have to do some calculations. So if I put in -1, that's going to give me 4 minus 4, which is 0. If I put in 0, I'm going to get -4. If I put in 1, I'm going to get 0. And if I put in 3/2, I'm actually going to get 5. Okay. Now, let me zoom back out for a moment, and let's take a look at the points that we have on this whole page. So I notice that I've got this point 0, -1 from the first equation that we took a look at. And in my second table, guess what point I also have? 0, -1. Okay. Let's see if there are any other points in common. -4, 0, -4, 0. 0, 1, 0, 1, and 5, 3/2, and 5, 3/2. At 0, 1, though, in the first equation, we had a t value of -2. But in the 0, 1 in the second set of parametric equations, the t value was -1. So it's the same point, but it happens at a different moment in time. 0, time of 0 gives you -4, 0. That's the same. But when I get to 0, 1, one time is at t equals 1, and one time is at t equals 2. And then for the last one, the time is 3/2, and this time is at 3. Okay. So remember earlier I said that a parametric curve can be defined by more than one set of parametric equations. This is an example of that, okay? These two equations, in example 1 and example 2, actually give you the same curve. They give you a sideways parabola, part of it, the same part, in fact, okay? It gives you the same equation, the same graph, but the difference is that in example 2, it happens twice as fast, okay? So what I mean by that is in example 1, it took how many seconds to create this graph? Okay. And how many seconds does it take to generate the second graph? Yeah, 2.5, right? Because we don't start at 0, we actually start at 1 beneath that. We start at -1. So the second set of equations might be useful if you were trying to model a system that moves more quickly. But if you have a system that moves more slowly, example 1 might be a better way to model that system, okay? And so one of the awesome features about parametric equations is you can not only create like a map of what the function or what the curve is going to do, but you can also incorporate how quickly it's going to cover that graph. Okay, so if you have a system that's moving faster, you can change the equation so that you get an equation that gets generated more quickly. But if you have one that moves more slowly, you can take one that you can generate a system of equations that eliminates that parameter in a way where you have the same graph, but it moves through it more slowly, okay? So it's not a mistake that example 1 and example 2 give you the same graph, just one of them happens twice as fast. All right. So let's move on to example number 3, okay? So example number 3 has some sines and cosines in it, all right? So we could have parametric equations that have trig functions in them, that's okay. And when we look at trig functions, we are looking mostly in terms of radians, and so a lot of times that the parameter interval will be set from 0 to 2 pi, but that's not always the case, all right? So in this equation, what we're going to take a look at is filling in our table, and we're going to plot a graph over to the right. And then we're going to talk about what it looks like to eliminate the parameter, okay? So let me give you maybe a moment or two to fill in this table and start to generate your graph, okay? And specifically, as you get to the graph, I want you to think about which direction are you going to draw those arrows in. Okay, so we really want to make sure we have arrows that tell us which direction we're tracing around the shape. All right. So hopefully your values look very similar to the values that I have here, that the x is going to start at 3, go all the way down to -3, and then come back up to 3. And that the y's are going to start at 0, go up to 3, go down to -3, and end at 0. Okay? Now, if you were in my pre-calc class, you know that I gave you a lot more values in between 0 and pi over 2 and pi, okay? But what I want us to kind of start to think about is like, how do we know, like, if we want to plot by points, what are some quote unquote good numbers that we could choose to plug in to our equations, okay? Now, when you're working with sine and cosine, I feel like all the half pi's, so 0, pi over 2, pi, 3 pi over 2, that gives you enough information to generate a good graph, okay? If you wanted to, you could certainly try plugging in values like pi over 3, pi over 6, and those are trig values you should definitely know, but we know that those aren't necessarily nice numbers to plot. So I just wanted to kind of think about, if we were doing this, you get to a test, you're like, I don't remember what shape this is, generate a table, but pick values that are going to be giving you nice answers. So if you see the trig, I wouldn't plug in 1, 2, 3, 4, 5, because that's not going to give you nice numbers. Whereas half pi's might give you enough to get started and just sketch a quick graph, okay? So let's plot these points. I'm going to start at 3, 0. Okay, so that's my starting point. Now the next point I plot tells me which direction I'm going in. 0, 3. So I know my arrows are going to go in the counterclockwise direction. Okay. Then I go to -3, 0, 0, -3, and I get back to 3, 0. So what shape should I be getting here?
Circle.
I should be getting a circle, okay? And we're gonna see at the end, I'll give you a summary table, that if these coefficients of sine and cosine are the same, you will end up with a circle, okay? So let's see how the brain is doing this morning, if I can draw a circle. All right, not bad for a Wednesday. I'll take that. All right, so, but I want to make sure that I draw in those arrowheads before I move away from the question. So it doesn't matter how many you put, I would say just put enough so that I can tell which direction you are going in, okay? All right, any questions about that graph? Okay. So let's talk about eliminating the parameters, okay? Now, like I said earlier, there are a lot of different ways to eliminate the parameters. However, we want our rectangular equation to look like a equation that we know how to graph. Okay, so when we eliminate the parameters, especially for the sine and cosine ones, I want us to follow these steps so that we can see what this actually looks like, okay? So this x equals 3 cosine t and y equals 3 sine t, okay? To eliminate the parameters involving sine and cosine, we're gonna go back to our Pythagorean identity that says sine squared theta plus cosine squared theta equals 1, okay? And let me write our equations down here. So everywhere I see a sine theta or a sine t, I can replace that with y over 3. Because if I just divide both sides by the 3, I get that. In order to find cosine t, I'm going to divide both sides by that coefficient, which gives me x over 3. Okay, now I'm going to take the x over 3 and the y over 3 and substitute it into the equation below. And so that's going to give me y over 3 squared plus x over 3 squared equals 1. If I square everything, I get this, plus x squared over 9 equals 1. And if we look at that, that is the special case of the ellipse, where from the center we go 3 out horizontally and we go 3 out vertically. That gives us a circle. But some of us might recognize the circle equation more if we write it like y squared plus x squared equals 9. And then we know that the radius is the square root of 9 or 3, okay? But for these sine and cosine ones, when we're eliminating the parameter, I would like us to do it this way so that we can confirm for ourselves what shape it is, okay? At the top here, I'm just going to squeeze in sort of what I've seen other folks do for eliminating the parameters. And the equation that you get is not mathematically wrong, but it doesn't help us identify what shape our graph should be, okay? So what I've seen some folks do is they say, well, I know that x divided by 3 is cosine t. So they have that part, but then they take it one step further and they say that t equals the arc cosine of x over 3. And they do the same thing for y. They get y over 3 equals sine t, and that t equals arc sine of y over 3. Okay? And so what people do is they take one of the t's, maybe this one, and they plug it in to the other equation. And you end up with something like y equals 3 sine of arc cosine of x over 3. Now, to me, this, when I look at it and someone's like, what shape is that? I'm like, I don't know. Okay? So that's why I don't want us to do it that way, because this does not help us figure out what shape it should be in case we forget looking at the parametric equation what shape it should be, okay? So it's not mathematically wrong, but it's not what I'm looking for, because I want us to be able to confirm, oh, okay, it's a circle. X squared plus y squared equals 9, okay? All right. So let's take a look at this equation right here. If we were to just look at the equation, 5 sine t and y equals 5 cosine t, what shape do you think we're going to get here?
Another circle?
Yeah, we're going to get a circle. And the radius?
Square root of 25?
Square root of 25, right? Okay, so let's make a quick XY table here. And froze on me in the middle. Okay, so let's make a quick XY table. And we're gonna go ahead and do that. So I've got t, I've got x, and y. Good idea to pick the same values that I used before? Probably, because I'm dealing with something that's very similar. So I'm gonna choose 0, I'm gonna choose pi over 2, pi, 3 pi over 2, and 2 pi, okay? So when I plug in 0 into the x equation, what value do I get?
0?
Get 0, good. So we're gonna get, for the x's, I believe we get 0, 5, 0, -5, 0. Whereas for the y values, when I plug in 0, because it's cosine, I'm actually going to start at 5, go down to 0, -5, 0, and 5. Okay? So if we were to sketch this on a rectangular coordinate system, we would indeed get a circle with a radius of 5, okay? And our starting point, though, is not going to be on the x-axis. Our starting point is actually up here at 0, 5, because that is the first value in my interval. Now, once you plot that first point, the second point gives you the direction. 5, 0, 0, -5, -5, 0, and back to where I started. So as I draw this, the shape might not be different than the previous one, but in our previous diagram, we went counterclockwise, whereas in this one, we want to go clockwise. Okay, so that is one of the other differences is sometimes the equation will look very similar, like this one has both a sine and a cosine, and they have the same number in front, like one has 3 and 3, the other one has 5 and 5, but the direction changes because I change which one is my x and which one is my y. Okay, so a couple questions in the chat. Will we need to indicate our starting point for tests and quizzes? I think I asked you just to generate the direction. So I'm just trying to make it explicit like how I chose that direction, okay? So you don't need to indicate your starting point, but please don't guess on your direction. Be like, I hope it's this way, I'll put it down. Like put some thought into it. And then the second question, if the range of the function was non-inclusive, would we leave the points on the graph open? Are you meaning like if there are discontinuities? Yeah, so we are assuming for these parametric equations that f and g are defined over our interval. So we're actually not looking at cases where you're going to have like an asymptote or a hole or anything like that. Okay, cool. All right, so let's take a look at eliminating some parameters and starting to think about what shapes might occur, okay? So let's take a look at example number 5, okay? So for 5, 6, 7, and 8, I want us to be eliminating the parameters, okay? So eliminating the parameters will be example 5 and 6 and 7 and 8, okay? So let's start with example number 5, okay? I hope that our fear of exponential functions like e to the x and e to the negative x has gone down a little bit since we started this course, because we've definitely used it a lot, okay? But just because we see the t's doesn't mean we need to panic here, and just because we see exponentials doesn't mean we need to panic. Let's actually take a few ideas on how we could get rid of the t's, okay? So anybody have any potential ideas on how to get rid of the t's in example 5?
Natural log.
I could natural log, yeah, because that's usually what we do when we see the exponentials, for sure. Okay, yep, I hear another person who's like natural log, so that's definitely one idea that we could do. All right, what are some other ideas that people have?
Square roots.
Why square roots?
Just a shot in the dark.
Could you multiply by e to the t?
Multiplying all the sides by e to the t?
Yeah.
And how would that help?
I was thinking of 1 over e to the t multiplied by e to the t would just equal 1, and then you would have 3e to the 2t.
Okay, okay. So thinking about exponent rules, I actually really like that part of what you said, that you could, how did you say you could write this again?
1 over e to the t.
1 over e to the t. Okay. So that's certainly one potential idea. All right, so let's do this. Let's try it both ways. Let's see what happens when we try and eliminate the parameters using natural log, and what happens if we use some exponent rules in here to simplify, okay? So natural log. So if I natural log the first equation, I'm going to get natural log of x equals negative t, right? Because the natural log of e just goes to 1. Folks who wanted to natural log, do you want to natural log both equations or just one of them?
Both.
Both? Okay. So if we natural log the other equation, we get natural log y equals, what do we get here? 3t. Okay. So how do we get rid of the t's from there? Because our goal is to get one equation that has no t's in it.
Use natural log to, like the rule we did with the basketball equation.
Can you clarify that?
So for example, if you take x would be the e to the negative t. No, never mind. I'm just in circles.
Okay. All right, so let's keep our goal in mind. We want to get rid of the t's. No more t's, only x's and y's. Okay, so I see that we could move that negative sign to the other side, so we actually get t equals negative natural log x, okay? And then if we follow that train of thinking, what should we do next?
Plug it into the 3t.
Plug it into the 3t. Okay, so everywhere where we see a t, we're going to replace it with negative natural log of x. Okay, so that would give me, these two together would give me natural log y equals negative 3 natural log x. Exactly. Okay. So have we eliminated the parameter? Yes, there are no more t's. So mathematically, this is correct. What shape is that? That's something I don't know that off the top of my head, what shape that is. Okay. So definitely mathematically possible. And I have to say this, I love that we are at a point where we're like, I see an E, to undo it, I need that natural log. Like, I think that's a really important algebraic concept to keep in that toolbox, okay? Let's try the other way and see what happens. So I'm gonna go back to this x equals e to the negative t. And instead of writing it like this, I forget who suggested it, but that idea of writing it as 1 over e to the t, because that's our definition of the negative exponent. So if I have this equation and I have this equation, okay, how can I get rid of the t's? Like, what kind of substitutions can I make here? And let me quantify that by saying without using natural logs. How can I get rid of this parameter without using natural log?
You can plug in y over 3 where that e to the t is.
Okay, so you isolated the e to the t in the second equation, and you said y over 3 equals e to the t. And then I think you said everywhere I see the y over e to the t, I put in y over 3. Okay, so these two together will give me x equals 1 over y over 3. All right. How else could I write this equation? Like if I wanted to simplify that a little bit.
X equal 3 over y.
Yeah, because the reciprocal is 1 over, I get 3 over y. Okay.
Y equals 1/3 x.
No. Yeah, if we're going to solve for y, we don't get 1/3 x, we get 3 over x. Okay. Now, is this a graph that we know what it looks like? And I hope the answer is yes. Okay. This should look a lot like that y equals 1 over x, except it has a vertical stretch of 3. So we end up with a case where it is a graph that looks, yeah, like that hyperbola, but it is rotated 45 degrees, right? So we have this is a graph that we know what it looks like. Might be a little bit nicer to have this as our equation rather than the first one we had, which is the natural log one. Okay. Now, someone had suggested, I believe it was Broy suggested that we actually, at this stage of this equation, that we e both sides so that we can get rid of the natural logs. And I think one thing we want to think about as we go through these eliminating parameters is we want to think of the smoothest way to get there. And so with the natural log idea, I think it's a great idea. I think you have to natural log and then you have to unnatural log, which makes it a little bit more clunky, but the concept is solid. And I think what I like about the second method is I didn't have to use natural logs at all. Instead, what I looked for was what was in common between the two equations. And I noticed that both terms have an e to the t. And so being able to isolate e to the t in both cases, that allows you to eliminate the parameter without looking too much into like algebra, like the natural log stuff, okay? It's kind of like in that one example earlier with the arc sign. You could do the arc sign, but does it help you get closer to an equation that you can recognize, or does it take you further away from that? Okay, so I would say for these, I know it's hard for me to sit here and say like, well, whatever is the easiest, because I think for some of us, natural log feels easy right off the bat, but we also want it to be like easy, but recognizable. So we need to find that sweet spot between being easy to eliminate the parameter and being able to recognize the shape of the graph that comes out of that, okay? So I wanted to start with example 5 because I think that's actually the toughest out of all of them, okay? But let's take a look at example number 6 here. if we want to eliminate the parameter here with the least amount of work, what could be a good starting point?
Move the 1 on the y side and then plug that value into the x.
Yeah, definitely. So that definitely came out in the chat as well. So this +1, let's move it to the y side, and we've already eliminated, or not eliminated, but we've already isolated t. That's awesome. So we get from here that t equals y minus 1. That means everywhere I see a t, I can replace it with y minus 1. So what does that give us? X equals 3 times y minus 1 minus 2. What shape is that?
A line?
Yeah, it's going to be a line. Perfect. Now, I know that we're used to having our equations as y equals. It is totally fine to leave it as x equals, okay? Now, part of the reason I want to kind of bring that up now is for those of you who are continuing on to differential equations, okay? So I know differential equations is a few courses away, but if you are one of those folks going on to differential equations, at some point, we need to be just as comfortable working with like an x equals as a y equals. And sometimes we even don't want to separate the x's and y's. We want to kind of keep them all mixed together. Okay, so I just want us to start to think about it's okay if we don't solve for y, because at some point we might be learning all this other complicated math where it's not worth it to solve for y. It might actually be easier in terms of x or something like that. Okay. You could certainly distribute and simplify here if you wanted. And if you did that, I think you get x equals 3y minus 5, which might be a more clear indication to you that it's a line, but it's not necessary. Okay, I think once we get to that x equals something y, we know it's a line, we can kind of stop there. All right, so let's do this. Let's take a break right now. So it is 10:28. Let's be back at 10:35. Okay, so we'll be back at 10:35. And I think the second half won't be quite as long as the first half. Okay, so my hope is to get you out of here a little early today. I know you guys have been working super hard. All right, so I'll see you back here in about 6 or 7 minutes. All right, folks, so we're gonna go ahead and jump back in. We've got 2 more examples where we're gonna look at eliminating the parameters. And then we're gonna look at, I made a chart of maybe some ways that you can restart to remember, like if I see this kind of equation, then this is the kind of shape that I will get. That's actually really handy for Calc 3. So for those of you who are moving on to Calc 3, this could be a good table to kind of have on hand for that class. And then we're gonna finish off the day with thinking about how can we, given one rectangular equation, come up with multiple different parametric equations that define that one curve, okay? So let's get started. All right. So before the break, we spent a good chunk of time talking about strategies for example number 5. And I think that was really valuable, okay? I hope it didn't feel like, oh, I was purposely not giving you the answer. Like, what I want us to talk about is like have a space to think about, like, well, why is this method maybe different than this method? Which one is going to serve me better in a different situation? Because that's the kind of thinking that's really going to take you far in math, which is that decision-making skills, okay? So let's go ahead and start with example number 7, okay? So for example number 7, I'll give you a moment to take a look at that, but it reads x equals the square root of t, and then plus 2 is not under that square root, okay? So that plus 2 is outside of the square root. And then we have y equals log of t. So what are some thoughts here? Take a moment, think about what strategies you might want to try for this, and then let's go from there.
Couldn't we move the 2 and then square both sides? And then
Okay.
plug it in to the y?
So move this 2 and then square both sides, okay? And what would we do after that?
Plug it into the y value, so log of that squared value.
Yeah, and then anywhere we see a t, we can substitute that over into the other side. Okay, any other ideas? Yep, we could use the idea of exponents to get the t out of the log. Yeah, so we could say that, so sorry, one first step is x minus 2 equals the square root of t. That's one possible first step. And then the other possible first step is we could say that t equals 10 to the power of y. Yeah, okay. Now, let's try both situations and see, okay? So let's try the first way first. So after we move that 2 over, I think, Mariah, you had said that we're going to square both sides, okay? And then everywhere we see the t in the y equation, so we're going to have y that is log of x minus 2 squared, okay? And given the properties of logs, I could actually write this as 2 log x minus 2. So this power comes down to the front like a coefficient. Okay? Now, when I look at that graph or that equation and I ask myself, can I visualize the graph of this? Yeah, I can, because I know the log graph. I know that minus 2 means we're going to move it to the right 2. And then that 2 in the front is just a vertical stretch. And so that's something that I can visualize. And so I would say, yeah, I think this first way works just fine. Okay. Now let's try the second way. So the second suggestion was that we rewrite our y in exponential form. So we get t equals 10 to the y. And everywhere we see a t, we're going to replace it with 10 to the y. And so for folks who suggested this one, did you want to just substitute this right under the square root? Or what were your thoughts on that?
I don't think they have much of a choice.
Okay, well, I think we could plug that in. So we get x equals the square root of 10 to the y plus 2. That's certainly an option. You know, I think it's possible maybe they like solved for t on the other end, and then they had x minus 2 squared equals 10 to the y. I think that's another option. Okay. But I would say that in this case, that second way actually doesn't really give me a clear visual of what that graph looks like, okay? I don't think that algebraically it's that much more challenging. I just don't know. I have a parabola on the left-hand side, I have an exponential on the right-hand side, and I'd need to figure out where that intersection point is. And so that's maybe not quite as friendly. Whereas I think the first way is a little bit more clear in saying like, okay, I know it's a log graph. I know it's shifted to the right too, and it's got this vertical stretch, okay? All right, we've got one last eliminating parameter right here, which is example 8, okay? And we see the sine and we see the cosine. So that should remind us of examples 3 and 4 where we had the sine and cosine. However, the thing that is different is that this number in front of the sine is different from this number, which is in front of the cosine. Thoughts on what shape is going to get generated here?
Is it the rows?
Ellipse.
I'm sorry?
An ellipse?
You said an ellipse, yeah. So when those numbers are different, you're going to end up with an ellipse, okay? So let me be a little bit more specific. You have the sine and you have the cosine. That's still there. However, the numbers in front are different from each other. That's going to give you an ellipse. So let's eliminate the parameter in the same way we did in the other one. So I'm going to divide the x1 by 4. I'm going to divide the y1 by 3. And I'm going to plug them into my Pythagorean identity, sine squared plus cosine squared equals 1. That's going to give me x over 4 squared plus y over 3 squared equals 1. And to further convince ourselves that we definitely have an ellipse, x squared over 16, that means I'm going to go up and down 4 in the, or sorry, side to side 4 in the x direction, plus y squared over 9 means I go up and down 3 from the center of 0, 0, and that equals 1. Okay. So again, when we are looking at these equations, I think what makes Calc 3 a little bit easier is if you can look at a parametric equation and say, I know what shape that is, okay? Because when you get to Calc 3, you're going to take these parametric equations that are just in 2 dimension, and you're going to start working with them in 3 dimension. So we're going to start to add different layers here, and the more solid your foundation is, like, oh, I know what curve that is, the easier it's going to be to now add a 3rd dimension onto whatever shape you're looking at, okay? All right, so that being said, here is a chart that I wish I had had when I was learning parametric equations. I tried to find like a chart somewhere online, and for some reason there is no chart online that is like this. So if you find one, let me know. But I think it's nice to think about patterns, because we throw all this new content at you and we're like, just remember these patterns, but we don't have the same amount of time to learn it like we did with lines and parabolas and all those other functions. Okay. So let's go through a few handy patterns. So anytime you have x and y, your parametric equations, and the parameter, or t, has the same degree, okay, such as x equals t minus 1 and y equals 2t plus 4. That's one example where both the parameter, like t in both of them, have a degree of 1, okay? What you're going to end up with is a line. Now, that also means you could have something like this: x equals t to the 1/3 and y equals 7t to the 1/3 minus 4. The degrees of t are the same in the x and the y. So even though this one looks more complicated, you're going to end up with a line, okay? It could be the same thing if you had like x equals t to the 14th and y equals something something t to the 14th. As long as you have the same degree, when you eliminate the parameters, you're going to end up with a power of 1, which gives you a line. All right. Now, this next two cases are very similar to each other. It's just a sort of a reversed order, okay? So if the power of x is the square root of the power of y, such as x equals 2t and y equals t squared minus 1, you're going to end up with a parabola. Okay, but more specifically, you're going to end up with one that is up or down. Another example might be if I had like x equals 3 times the square root of t. What would the power of t have to be in the y equation? So if I had like 5t minus 6, okay, the power of t in the first one is the square root of the power of y, of t in the y equation. So I'm going to end up with a parabola. So it's not necessarily the power you see is the power you're going to get. It's what's the relationship between the powers of x and y. All right, well, what if we flip those? What if the power of y is the square root of the power of x, like we have down below? All I did was switch the powers, so the square is in the x and the non-square is in the y. Well, that's going to give you a parabola again, but it's going to be facing either right or left. Okay.
Professor, sorry. For the one before that one, you said the power of x of t is the square root of the power of y of t. The square root of 2 is not 1. Is it? Like for the x, like the one before that one, 2t, and then t squared?
Yeah, I know what you're saying. So you're thinking about like once you sub that in, do you get the square root? Like what is the root for the 2 is the square root.
Like you mean like, what is this? Can you say that one more time? Sorry.
So if I have something squared, what is the square root of that something squared?
That something squared.
The square root of something squared is just that something.
They cancel each other out, right?
Right. So the square root of t squared is t.
Oh, I was just thinking of the power. So the
That
t
makes
is
sense?
included. Okay, yeah, I got it.
Yeah. So like the square
Okay.
root of that gives you the power. Yeah.
Gotcha. Thank you.
And you know what? I'm glad you asked though, because honestly, like this is a chart that I'm like, I kind of made up myself. And so I'm thinking like, what's the best language? And so it sounds like maybe I need to look at the language of this a little bit more clearly. So thank you for that.
Yeah, I think it would be like the square root of the t and the power.
Okay.
Because I was just thinking.
The power is like half of the other power. Does that work?
I don't know if it would work for every power, but for this one, yeah.
Okay. All right. So if we switch that idea, right, the power of y is smaller than the power of x, then we end up with a parabola that opens left and right instead. Okay. So maybe another example of this would be x equals, we could just switch what we had from before. And that would give us same kind of shape, parabola, but facing a different orientation.
Quick question.
Yes, what's up?
Is there any way to tell before solving it whether or not it's going to go up or down, or left or right? Or you just kind of find that out after you eliminate the parameters?
I think to answer that question, I would encourage you to try a few of those and kind of see. Because I bet that once you see like a few negative signs here or there, that might help you tell which direction it's going to open in. Right? Because we know if the t squared is positive, then it's going to open in a certain direction. But if we substitute in a negative value there, that might change that direction.
Got it.
Okay. Or if we had like 3 minus t squared instead of t squared minus 3, that would change the direction. Okay. So these next two cases we've already kind of taken a look at. Okay. We've taken a look at a case where x of t is a cosine t and y is a sine t, or we switch them. And what was the difference when we switched the sine and the cosine?
They're make each other opposites.
Can you be more specific? What do you mean by opposite?
Rotation.
Like they have alternating pattern.
But what does that change about your graph?
Positives and negatives.
Kind of headed in the right direction. Yeah, it's the direction in which we draw that graph. Okay, so the direction is going to be different if I have x as cosine or x as sine, but it won't change that the shape is going to be a circle. Okay. Now, the key here, though, is that the numbers in the front, those coefficients have to be the same. So in x equals 3 cosine t and y equals 3 sine t, I know that that 3 gives me the radius of the circle. But if I switch them and say x equals like 7 sine t and y equals 7 cosine t, then we're going to end up with a circle. It's just going to go, or we're going to trace it in the other direction. Okay. Now, if we have different coefficients, so a cosine and b sine, or the other way around, a sine and b cosine, we're going to end up with an ellipse. Okay, so same coefficients mean that we're looking at a circle. Different coefficients mean we're looking at an ellipse. And so maybe another example could be if we just switch those. So 7 sine t and y equals 3 cosine t. All right, so one of those will give us an Ernie ellipse and the other one will give us a Bert ellipse. So the distance that we're traveling is different, but also the direction in which we're moving is going to be different. Okay.
On the circle one, you have values of 7 on both.
Yep.
Where did that come from? It's just an example, right?
Yeah.
Okay.
Yeah, so you could certainly write down other examples, but I wanted to just have one where we could kind of extend that pattern a little bit. All right, last but not least, if you have a situation where you have the secant and a tangent, okay? So secant and tangent, that is going to give us a hyperbola. All right? Secant and tangent, or tangent and secant, will end up with a hyperbola. And you could make up whatever numbers you want for your a and your b, and you could switch your secant and your tangent, and that would give you just a second example of what the hyperbola equations could look like in parametric form. Okay. So even something like this would give you a hyperbola because 4 is not equal to 1. And we end up with the tangent and the secant, okay? Now, we didn't do an example like this, but how would we set up our, if we wanted to eliminate the parameters for something that had a secant and tangent, how would we approach that?
Can you just switch everything into sine cosine?
You could, that's certainly one option. What other ideas do we have?
Pythagorean identity.
Okay, but which one?
What is it? Tangent squared minus 1 equals secant squared?
Close.
Or
We
1
got
plus tangent squared?
tangent squared plus 1 is going to give us the secant squared. Okay, so the secant and tangent get paired together, so we want to think, yeah, we could do that identity. Yeah, exactly. And I think it might even be more helpful to think about it secant squared minus tangent squared theta equal, or tangent t equals 1. All right, because I just moved that tangent squared to the other side, and look what we have. We're going to end up with a fraction minus another fraction equals 1. Well, that's going to give us a hyperbola. All right. So all that stuff we learned in the last chapter, there are other ways to represent those equations. All right. And sometimes it's going to be easier to work in parametric, and sometimes it'll be easier to work with rectangular. It's just it'll be different setups for the different problems. Okay. So let's finish off here with talking about multiple representations of rectangular equations, okay? And so what we're gonna do is we're gonna take a look at one rectangular equation, and we're gonna try and list a few different ways of writing that equation in parametric, okay? Now for right now, because we're just sort of setting a foundation for this, we're just gonna kind of be creative and think about all the different ways that we could write it. But when you're applying these in the future, you want to think about like what ways might be more useful than others, and that's going to depend on the context of your situation, okay? So example 9, find two different pairs of parametric equations to represent the graph of y equals 2x squared minus 3, okay? So we're going to go with the most basic option first, all right? The most basic option is you can let one of your x, either x or y, equal the parameter. What that means is the y equation that goes with it is just going to be 2t squared minus 3. Okay? Because if I plug everywhere I see a t, I plug in x, I'm going to get y equals 2x squared minus 3. Okay? So this is always an option. It's the most basic option, but that doesn't make it a bad one. Okay? Would it be valid to write this?
No.
No,
No, why not?
because it flips the graph.
Yeah, exactly. It flips the graph. It changes the x's and y's. So whatever whatever is already solved for, that's probably not the one to make your t. Okay, if you're looking for the basic option. The variable that's in the equation already, like the x squared, that x is the best option to have as your t, because now you just replace everywhere you see a t, you put the x, and then you've got your equation. Very straightforward. Okay, so this one, let's give it a big red X through it because that's not an option. Okay, but here's what might be another option if you want to be a little bit fancier. You could say x equals 2t. So you could put like a constant in front of that. Okay. what would that give us as the y?
Y equals 8t squared minus 3.
Ah, how did you get that? Back up a few steps for us. How did you get the 8?
When you plug the 2t into where x is, you get 4t squared. That times 2.
Okay, so you actually plug this in to help you find the second equation. All right, so this would give us 2 times 4t squared minus 3, or y equals 8t squared minus 3. Yeah, okay. So whatever you plug in here, you want to make sure that it's going to give you that, like, plug it into your other equation and then just bring it all the way through, okay? What if I said x equals sine t? Like, let's say for whatever context I'm working in, that the trig might be helpful. How could I create the other parametric equation that goes with this one?
Wouldn't
Would
you
it
just,
be? Go for it.
I was going back towards identities.
I don't think you need the identities here.
What
It's
did you do?
2 sine squared t minus 3.
Yeah, we can literally take sine t and plug that in. So we get 2 sine t squared minus 3. Because look what happens when we substitute. Everywhere we see a sine t, if we put in x, we'll get 2x squared minus 3. Okay? So you might want to write it like this. All right, but that is a very small detail here. I think the bigger thing to focus on is that whatever you choose for your x, you just plug that in wherever the x is in the rectangular equation, and that's it for your y. Okay.
Why did the 3 go from negative to positive?
Sorry, that's supposed to be a minus.
Thank you.
All right, so I know this question asked us to do 2 different pairs of parametric equations. We did 3 here because we've got this one over here as well, okay? But I just wanted us to see the pattern that, like, whatever we choose as our x, we can, as long as we substitute that into the y equation, we can generate another y that goes with that x, okay?
I have a question.
Yes, sir.
Will we ever be taking the integrals of these parametric equations?
We are going to look a little bit at some applications of parametric equations tomorrow. So we'll take a look at slope and we'll take a look at area.
Okay. Will it ever be an advantage to make your x a trig function in order to plug it in? Like, I was just wondering why.
Yeah, I just wanted to show us that like you could do that, right? You could put an e in there, you could put a natural log in there, you could put whatever function might serve you best. In the context of what we're going to be working with, I think we're going to stick more to some of the trig and some of the polynomials. So we're not really going to go much beyond that, but just in case, like, it's not limited to those, it could be any function you want to put in there.
I'll take it.
Okay. All right, one last equation or example here. Example 10. Find 3 parametrizations for the line of slope m through the point x1 comma y1. So this word is just a really fancy way of saying find some parametric equations. In fact, find 3 pairs of parametric equations that satisfy these constraints, okay? So the first thing I'm going to do is I'm going to write out the rectangular equation that goes with the slope and the point, kind of like how I had y equals 2x squared minus 3 in the beginning for number 9. So when I write that rectangular equation, I'm going to get y minus y1 equals mx minus x1. Okay, so this is my rectangular equation. And what I want to do is come up with a few parametric equations that I can use to represent this rectangular equation. So let's start off with the most basic one. We could say that x equals t, and then that would give us y minus y1 equals mt minus x1. Now keep in mind that x1 and y1 are it's point, right? So x1 is a number, y1 is a number. So it's okay that I have those in there still. I'm not mixing the x's and y's and t's. It's x1 is a random number and y1 is a random number, okay? So this is one option, and that's our most basic option, right? It doesn't make it a bad one, but it's a good place to start so that now we can think, okay, everywhere I see whatever I put here, I need to put it in that same spot. So maybe what I could do is replace that with I don't know, a different function, okay? So maybe like the last one, I'm like, oh, maybe sine is good in this case. I'm not really sure. And I could try like x equals sine t. And that would make this y minus y1 equals m sine t minus x1. Okay, so this could be another option. And I follow this same pattern where whatever I plug in for that goes in the same place that I want to substitute that x into to get back to my original. Now we could continue this pattern and say like, oh, let's just be creative about whatever functions we want to plug in there. But sometimes we like to take not just that one, but sort of, if we know we're subtracting a constant, we just call the whole thing t. So what I mean by that is we could say that x minus x1, so the whole thing in the parentheses, x minus that number is t. Now, if I call x minus x1 equals t, what is the y equation that goes with that x equation?
Divided by slope.
Y minus
Sorry, go ahead.
y1. Y minus y1 equals m to t times t.
T, yeah. I'm following that same idea that whatever I'm substituting needs to go in for the t. And I can see that that's going to get me back to the original, okay? So this would be a third way of potentially defining a set of parametric equations that satisfy, here's the line, okay? Now, we could throw a different trig function in there. We don't have to use sine, okay? So it might be something where we're like, oh, x minus x1, let's call it tangent because that applies to whatever situation we're looking at. Then the only thing that would change between this one and this one, we'd still have our y minus y1, but we have m tan t, okay? So even though this asks for 3, here's 4, just so we can kind of see like some different ways of substituting in to find that parametrization. All right. I know I'm talking a lot about like, here are some like different scenarios. It might be more useful in this scenario versus that scenario. That's not something we're going to have to worry about. I just want to start to like get you thinking that there can be more than one way, and that eventually more than one way, what you'll get to choose which one might be more useful. Okay, but that's not a choice we'll have to make in this particular. All right, so that is it for today. Are there any questions on 13.1?
Should we put that chart on our cheat sheet?
Up to you. It could be useful for you. Yeah. So now that you've seen a couple tests and thinking about what might be useful versus what might not be, I'd like you guys to kind of start making those decisions about what will be useful for you. Okay.
I have a question on quiz 7 if nobody has questions on this.
Okay. All right, so I'm going to stop my share here then. What was your question on quiz 7?
For the last problem,
Yeah.
I don't have it in front of me. Hold on. Well, it's the last problem. It was just the equation that we're given. I noticed that the last part was.
It should be 80y.
Oh, okay. I
Yeah.
thought I missed something and we just.
No. I thought I had changed that on the answer key online, but I don't know. Like sometimes when I upload files, they don't go through. So
I can delete that. Oh no.